Hi everyone, I'm Arun Govind from Simunetics. Today, I'm excited to launch a new video series focused on data-driven optimization techniques using deep learning. This approach is rapidly transforming how we solve problems across engineering and applied sciences. You've probably encountered data-driven methods already, often without even realizing it. In medical imaging, for example, MRI and CT scanners use recorded signals, such as electromagnetic pulses or pressure responses, to reconstruct images of internal organs and tumors. This is a classic inverse problem. In petroleum engineering, we send seismic or sonar waves into the Earth and reconstruct detailed geological structures from their reflections. In fluid dynamics, especially turbulence modeling, we use high-fidelity, direct numerical simulation, or DNS data, to calibrate faster and more practical LES and RANS models. And in climate and atmospheric science, data-driven models help bridge the gap between micro-scale physics, like condensation, and macro-scale variables, such as temperature and velocity, where traditional closed-form models often struggle. In this video series, we will focus specifically on numerical scheme optimization. Imagine designing a numerical scheme that is highly accurate yet introduces minimal numerical dissipation. Instead of hand-tuning parameters, we use data-driven optimization to discover the optimal balance automatically. Here's the roadmap for this series. First, we'll cover the basics, optimizing a simple PDE solver by minimizing error using analytical solutions and data. Next, I'll introduce adjoint methods. These form the backbone of control theory, shape optimization, and topology optimization, especially in aerodynamics. Finally, we'll move to deep learning integration. We'll optimize a turbulence closure model using modern frameworks like TensorFlow and PyTorch, and I'll also show how similar ideas were implemented back in the 1990s using classical adjoint techniques.
Honestly, I wish I had mastered these ideas during my PhD. At that time, I relied heavily on parametric optimization, which is far more manual and time-consuming. During my research, we developed numerical frameworks for high-speed compressible flows, focusing on WENO schemes, weighted essentially non-oscillatory methods. We introduced a variant called WENO-OA, which reduced computational cost by about 75% compared to classical WENO schemes for the same error level. Later, we achieved similar accuracy using 6 times fewer grid cells than traditional methods. However, we eventually hit a wall. While we observed massive improvements in two-dimensional problems, such as shock-shear layer interactions and double Mach reflection cases, we saw almost no improvement in simple one-dimensional shock tube problems. In fact, most so-called novel numerical schemes today only marginally outperform the 30-year-old WENO-JS benchmark. This stagnation is exactly what motivates me to explore data-driven approaches for numerical method design. In the next video, we'll start with a hands-on demo using the Euler equations. We'll begin with first-order schemes that, surprisingly, can already produce high-resolution results when optimized correctly. You can generalize this procedure and convert this to a publishable research. I'll share all the scripts in the video description. Traditionally, we rely on Runge-Kutta methods for stability, but they're computationally expensive. An RK3 scheme costs roughly 3 times more than a simple forward Euler step. So the question is, can we stabilize a cheaper, simpler scheme? Specifically, we'll explore a forward-in-time, central-in-space method stabilized using artificial dissipation optimized by data and still obtain high-resolution results. To keep things simple, we'll start with the one-dimensional linear convection equation using a Gaussian initial condition. From there, we'll move on to the Euler equations. We'll test several spatial discretizations, forward in time with backward in space, forward in time with forward in space, and forward in time with central in space. The first scheme is conditionally stable, the others are unstable. We'll explore whether we can stabilize these unstable schemes using artificial dissipation, both with and without neural networks. If this sounds interesting, you're in the right place. Let's begin.
In this presentation, I will discuss the stabilization of the forward time, forward space scheme for the one-dimensional wave equation. We will examine why FTFS is unstable, how scalar dissipation stabilizes it, and how optimization improves accuracy. We consider the one-dimensional linear wave equation. The solution evolves in time while being transported at a constant speed. The initial condition is a Gaussian pulse. Our objective is to stabilize the FTFS scheme using scalar dissipation and compare it with the stable FTBS scheme and the exact solution. Let us now look at common numerical schemes used for linear advection. First, the forward time, backward space scheme, or FTBS. This is an upwind scheme and is conditionally stable under the CFL condition. Next, the forward time, forward space scheme, or FTFS. Although simple, FTFS is unconditionally unstable for linear advection. Similarly, the forward time central space scheme, or FTCS, is also unstable. This instability motivates the need for stabilization. To stabilize FTFS, we introduce a second-order scalar dissipation term. This term acts as artificial diffusion. The dissipation coefficient, alpha, controls the amount of numerical damping. With a suitable choice of alpha, spurious oscillations are suppressed and the scheme becomes stable. To quantify accuracy, we use standard error metrics. These include the root mean square error, the L1 norm, and the L infinity norm. These errors measure the difference between the numerical solution and the exact solution. The root mean square error is used as the objective function for optimization. Our goal is to find the optimal value of alpha that minimizes the root mean square error. We use differential evolution, a population-based global optimization method. Differential evolution is well suited for non-convex and non-differentiable objective functions. The search is performed within bounded limits for alpha. The overall computational workflow proceeds as follows. First, we initialize the grid and the initial condition. Next, we compute the FTBS solution. Then, we compute the FTFS solution with scalar dissipation. The RMS error is evaluated and differential evolution is used to optimize alpha. Finally, we compare the optimized FTFS solution with FTBS and the exact solution. To conclude, FTFS and FTCS schemes are inherently unstable for linear advection. However, FTFS can be stabilized effectively using scalar dissipation. Optimization enables the selection of an optimal dissipation coefficient. The optimized FTFS solution achieves lower errors than FTBS. This framework can be extended to other hyperbolic partial differential equations and numerical schemes. This code demonstrates how to stabilize the forward time, forward space scheme for the one-dimensional linear wave equation. First, we define the physical and numerical parameters, including the wave speed, domain length, grid resolution, and the CFL number. A Gaussian pulse is used as the initial condition, and the exact solution is obtained by shifting this pulse according to the wave speed. We then implement two numerical schemes. The first is the forward time backward space, or FTBS, which is a stable upwind method and serves as a reference solution.
The second is the forward time forward space, or FTFS, augmented with a second-order scalar dissipation term. The dissipation coefficient, alpha, controls the amount of numerical damping. To evaluate accuracy, we define standard error metrics, including RMS, L1, and L-infinity norms. The RMS error is used as the objective function in an optimization problem. Differential evolution is applied to automatically determine the optimal value of alpha that minimizes this error. Using the optimized alpha, we compute the stabilized FTFS solution and compare it with FTBS and the exact solution. Finally, the results are visualized, showing that the optimized FTFS scheme remains stable and achieves lower errors than the standard upwind method.
We have found an optimal alpha for this case, but the key question is it applicable to different initial conditions, different grids, and different time steps? The answer is no. Unless we find a better closed-form model that works across different grids and initial conditions, this result is essentially useless. So now we enter the modeling part. In theory, the optimal alpha can be derived using von Neumann's stability analysis. However, instead of a purely analytical route, we use data to learn an approximate model. To do this, we must first understand which factors influence the optimal alpha. When we change the initial condition, alpha does not change. When we change the grid size, alpha does not change significantly. But when we change the CFL number, alpha changes noticeably. This tells us that alpha is a strong function of the CFL number and only a weak function of the wave number of the solution and the grid size. Another way to identify such independent or invariant parameters is by using the Buckingham pi theorem. This gives us non-dimensional groups such as the CFL number and K times H. Finding the correct independent parameters is an art in mathematical modeling. If we choose the right parameters, we gain generalizability. If not, we lose it. In our case, the optimal alpha is only a weak function of K times the grid size because most of our simulations are well within the Nyquist limit. We now use pi-SINDY to discover an empirical relationship. We do this by simulating the system for different values of KH and the CFL number, and then testing the model on different initial conditions. The code for this experiment is shared in the description. The results show that our approximate model for the optimal alpha generalizes to other initial conditions. The figure shown above illustrates the solution of the linear convection equation using wavelets. Notice that this initial condition was never used during training, and yet the model still works.
So here's the takeaway. An optimal parameter that works for one simulation is meaningless unless it generalizes. In our case, alpha depends primarily on the CFL number, with only a weak dependence on the wave number of the solution. Because this relationship is low-dimensional, using a neural network here does not provide any real advantage. By discovering the right invariance and learning a compact empirical model, we achieve stability without tuning for every new case. That's the real power of data-driven numerical modeling. In the next video, we move to the Euler equations, where neural networks do become useful. Check the description for the full code and subscribe if you want more deep dives like this. Thank you for watching.